All right.
So you're recording your voice or the action?
Everything.
Oh my god, this is what they used to make those instructional videos.
Yeah.
Right.
Yeah.
But we're doing it live because we can. Because somebody's missing this class and the class this afternoon, and we're introducing something that you don't want to miss anything from. So if you're thinking to yourself, how does the unit circle work? You can just pop online and review this moment. You'll get to relive this moment in time right now. And you're going to get to this video. If you talk clearly.
20 years from now. I'm just kidding, I was going to say a story.
Well, yeah, so that would have been picked up. All right, so here we go. The unit circle. Everybody, how about a piece of paper? New piece of paper, new notes. And give yourself a little coordinate plane. Give yourself a coordinate plane, okay? And if we think back to some of the work that we did last year when we were looking at tangents and everything, right? We can sort of recall that we would put an angle on a coordinate plane, and then there was a great big circle kind of, and then to find the slope angles, we had some piece here. You do not have to copy this down with tick marks, and you'd extend the angle, and then find this length and find this length, right? That all kind of comes back to us, right? Okay. So the idea stems from the fact that you can show an angle on a coordinate plane, right? So here's an x and here's a y. That's probably worth labeling, right? Give yourself a little coordinate there. So we know we're just dealing with that same little coordinate plane that we've run into before, okay? And we can draw and express angles on the coordinate plane, okay? So if I wanted to draw, say, that looks about maybe 40 degrees, I can express this 40-degree angle on a coordinate plane, okay? Notice, it is opening up counterclockwise, right? And it's a positive angle.
Should we be writing?
Yeah, you can make a note of this. You can kind of give yourself an angle, counterclockwise, positive, okay? But remember, we're recording, so if it doesn't get down, it's not the end of the world. So, if an angle opens in the counterclockwise direction, it is a positive angle, okay? So, if I wanted, I could have an angle. Let's say I've got this going on here. We'll use. So let's say my angle is opening positively. What angle would this be? 90. What angle would that be?
180.
180. What angle would that be? 180 plus 90 is 270. So an angle could come all the way around, and this would be about 300 degrees. This would be a 300-degree angle. What's even crazier is conceivably here, I could have an even larger angle. I can go even, in fact, greater than 360, right? I can go all the way around and then some more even, right? So I can have an angle, goes around once and back up here. We call this, 420 degrees, right? 360, right? The 360 plus another 60 would be 420 degrees. And it's opening in the positive direction, right? The counterclockwise direction. It's gone around 360 degrees plus another 60, and now it's at 420 degrees. If I wanted, do Do we think I could make a negative angle? Go the other way. Perfect. If an angle opens counterclockwise, or sorry, this is regular clockwise. If an angle opens clockwise, it's negative, right? So this would be like negative 60 degrees. Yes, you can have negative angles. Okay. My final question. Where is 0 degrees? If you want to show me a 0 degree angle, where would that angle be? What do we think? Claire, what are we thinking?
Like horizontal.
Yeah. Yeah, like horizontal, and in which direction?
To the right.
Yeah, right? If this is the angle right here, that's 0 degrees. 0 degrees is always to the right in the positive x direction and right along the x-axis. That is 0 degrees. You always start from this 0 degree. Okay? So, I want you, on your own coordinate planes, to sketch the following angles. Okay, so you're going to make a bunch of different little coordinate Cartesian crosses. Okay, and you're going to write the following angles. Okay. So go ahead and write these angles, and we will do them together in a quick second. All right, great. 120 degrees. You might have to, like, demonstrate it with your hands, since some people are, like, sitting down. Shane does this with her arm, opening up in a counterclockwise motion, right? So 120 degrees would be up past 90 by another 30 degrees. Note that I'm using this arrow to connote, really, just to be really super clear on like where the angle is opening up. I like an arrow. You don't need it, and you won't always see it with an arrow, but I like the arrow. Indeed, this is 120 degrees. 190, Aaron. Nice. So Aaron says go past the negative sort of direction of the x-axis by a lot or by a little or by just a little bit, kind of like that? Yeah. I love it. Past the 180 mark, which would be here, by 10 more degrees. Nice, Aaron. Great. Oh. Cool. 60. Yeah. Yeah, okay. 60, we got that. There's 60, again, with the arrow, if you're into that. How about negative 45? Bonnie?
It will be half of the, block, or, corner. Right.
Half of which one?
The one on the bottom.
Right. So Bonnie says, well, this would be, it would go into the lower quadrant here, quadrant 4 if we're being technical. It would go down by 45 degrees, and this would be negative 45 degrees. It's opening in the negative or clockwise direction. What about 315? Kira.
It's actually in the same place as
Whoa.
45, but it's like, instead of drawing the arrow going downwards, you draw it coming all the way around the origin.
Nice. So 315 degrees and negative 45 degrees. They kind of point you in the same direction, right? They're pointing the same direction. They share a number of properties. There are a lot of things that 315 degrees and negative 45 degrees have in common. Not the least of which, as Kira says, is they go in the same place, right? They're different angles, but they go in the same direction, which is an interesting piece. They're going to have other things in common.
Are they considered?
Wait, isn't that the opposite?
They're not considered reciprocals. And I wouldn't say that they're the opposite because they're actually heading, right? They're pointing in the same direction.
Would opposite be like negative 45 and 45?
Yeah, those would be opposite sort of in a numerical sense, yeah, absolutely, absolutely, absolutely. And they would share properties as well. All right. So this is good. This is great that we're asking these questions about, what is up with these two things being equal? What's the same? What's different? And to help us think about this, we're going to use this thing called the unit circle. Okay. So sketch another Cartesian piece here. And what I want you to do is draw a circle with a radius. So we want a circle. Radius equals 1, and the center is at the origin. A circle, I'll let you sketch it, then we'll see how close yours is to mine. Okay, a circle with a radius of 1, and the center at 0, 0. 1, 1, 1, 2. Circle. My poorly drawn circle. This is the unit circle. So make sure that you've got both Cartesian plane and a circle with a radius of 1 that's centered at 0, 0. All right, so now, questions? No, okay. So this is the unit circle. And the unit circle has some pretty cool properties that we're going to check out sort of right now. Okay. So if I wanted, on my unit circle, copy, paste it here. On my unit circle, if I wanted, I could place an angle, right? Just like we showed that you could show an angle and say, okay, here's the angle, right? I can throw up an angle on my unit circle like so. Why don't you do the same? So I've got some angle. I'm going to call this angle theta. Remembering theta from before. Theta, and we often use it as a variable for an angle. Okay, so we've got some angle theta. So far, so good, right? So again, make sure you've got that angle theta. And we note that theta, this angle, intersects the circle, the unit circle at this point, right? We see where that angle actually intersects the circle, correct? Label this point just x, comma, y, right? Because it's a point on a Cartesian plane, right? Every point on a Cartesian plane we denote with, an x and a y. So far, so good, right? Okay, and now what I want you to do is drop a little perpendicular right here. Drop a perpendicular from x comma y down to that point. Drop a perpendicular, indeed. So now, what three-sided figure are we looking at right here?
Right
triangle.
A right triangle. Interesting. Interesting. So what we've got is this right triangle, just to be explicit, this right triangle here. Whoop, got the wrong piece. There we go. This right triangle with a right angle. This angle right here is what? Theta. Now, what about the lengths? I'm going to blow it up just a little bit. What about the lengths of this right triangle? How long is the horizontal leg? How long is the vertical leg? And how long is the hypotenuse? Emily. The hypotenuse is 1 because it is the radius of the unit circle. Jonah, do we know any of the other lengths? Yeah, you could figure it out. Here's something for us. You're going to figure it out right now. This point, right, is x comma y, which means that this distance is equal to what? X. So this distance is x, right? It's the x coordinate. Not only is it the length right here, but it's also the coordinate of that point. So what would this other vertical length be? Y. It's the y length. Okay? Do we see that? Yeah? So, we see that on a unit circle, any triangle, any angle, right? If I pick a different angle, I can still represent it on the unit circle, right? And there's still some point, x comma y, right? For a different angle. No matter where the angle goes, there's always some coordinate at which it intersects that is x comma y, right? Right. In this case, x would be negative. But I'm still just calling it x to denote that there's like some x coordinate and then a y coordinate. But indeed, x would be negative. Nice. So the last piece I have for us here with the unit circle. And this is key. This is like the big money maker. What is the sine of angle theta?
Oh, sorry.
Equals y over 1 equals what?
Y.
The sine of angle theta is equal to y, is equal to the y coordinate that the angle intercepts on the circle, right? What about the cosine of theta? What would that be? Right, because cosine is adjacent over hypotenuse, so that would just be x over 1 or just x. Huge. Okay. What would the tangent be? Yeah, why stop here? The tangent of theta would be, well, opposite y over adjacent x. Interesting. Okay. Or if we think back kind of to back in the day, right? We remember that we used a circle very akin to the unit circle. In fact, it was like a 10-unit circle if we think back. And we said that the tangent of an angle could also be equal to, right, this length right here. We'll call it z, okay? And this length right here would be what? So again, looking at this new kind of right triangle that we made here, this length right here would be 1. Thus, z would be the tangent. Z over 1 would be the tangent. So z would also equal the tangent of theta, which would be the same thing as the ratio of y over x, because, of course, it's got that same ratio here and here as here and here. Oh, unplug. Plug it back in. Okay, so today we're going to be using what we know about what we just learned about the unit circle, sort of how it works, these three key ideas right here, and what we recall about our special right triangles, half squares and half equilaterals, to actually find sine, cosine, and tangent of different angles using the unit circle. So let's turn to page, I believe it is 6 in our packet. And see if you and your groups can get to work on finding point A, the coordinates for point A. So again, there'll be like coordinates there. And then the coordinates for point B. on each of these.